Good morning, all. Welcome to third day of Gyan workshop on Biocomposites 2025. Let's begin our first session. I invite Professor Allen to deliver his lecture on processing of bio-nanocomposites. Over to you, sir.
So the first question is why using cellulose nanomaterial, or it can be chitin or starch nanomaterials also, for composite application. So there are some properties which are interesting for this application. The first one is the high specific surface area. You remember, few hundred square meter per gram. This is important for an effective stress transfer at the interface between the matrix and the reinforcement. The aspect ratio is also important. We'll see later why. So remember that it ranges from 10 to 100 for cellulose nanocrystals, depending on the source of cellulose and on the hydrolysis, acid hydrolysis condition. And for cellulose nanofibril, it's much higher. So the stiffness is, of course, important. 100 gigapascal for the modulus for cellulose nanofibrils, 130 on average gigapascal for cellulose nanocrystals. This is important, but we'll see that maybe it's not the most important. So it's a lightweight material. This is important also for composite application. And we can easily tune the surface of these nanoparticles to promote some interaction, for example, with the matrix. So the main issue when dealing with nanoparticle is the homogeneous dispersion of this nanoparticle in a continuous medium. Because as the size of the particle decreases, the surface energy increases, meaning that these particles have a tendency to agglomeration. We can have different situations, which are reported here, that involve dispersion and distribution. We can have a poor dispersion and a poor distribution, meaning that you can see that we have aggregate, and these aggregates are not homogeneously distributed in the matrix. Poor dispersion, so still aggregate, but good distribution, so homogeneous distribution of this aggregate. Good dispersion, no more aggregate, but poor distribution, and of course, the objective is to have a good dispersion and a good distribution. So you have a report here, the main strategies that can be used to prepare nanocomposite from these cellulose nanoparticles in a liquid medium. This is what we will see now, or with dry nanoparticle, it will be the second part. Remember that these cellulose or starch or chitin nanoparticles are obtained as aqueous dispersion. And these dispersion are stable because of the sulfate group in the case of cellulose nanocrystals, when using, of course, sulfuric acid for the hydrolysis, and because of residual hemicellulose, few percent only, in the case of cellulose nanofibrils. This aqueous dispersion is stable, meaning that we can take advantage of this stability to prepare nanocomposite. So it means that we can use a water-soluble polymer or a polymer in the form of a latex. The processing is very easy. It just consists in mixing the aqueous dispersion of cellulose with the solution or the dispersion of the polymer, and then by different techniques, so you have experiment casting evaporation Monday afternoon, or by electrospinning, or by layer assembly, or by other technique, we can eliminate the liquid medium and obtain solid nanocomposite film. This is, of course, the easiest way. And I will show you some results that have been obtained. First, before that, it's important to note that when considering a two-phase material or multi-phase material, so it can be a composite, it can be also a polymer blend, there are four important parameters that will impact the properties of the composite. The first one is, of course, the specific behavior of each phase. The second one is the composition, the volume fraction of each phase. The interfacial properties are also important, of course, but not only. There is an important parameter, which is the morphology. The morphology in the sense of spatial arrangement of the phases. To understand this, we can consider a blend of two polymers, polystyrene and natural rubber. So polystyrene is a stiff polymer at room temperature because the Tg is around 90, 100 degrees Celsius, so it's above room temperature. And you know that natural rubber is soft because the Tg is below room temperature, around minus 60 degrees. We can consider that we mix these two polymers, 50% of each. We'll have the same phase. 50% polystyrene, and natural rubber, the same composition, 50% of each. Of course, the interaction between natural rubber and polystyrene are the same, whatever the morphology, but we can have two different morphology which are reported here. In this case, natural rubber is the matrix, and polystyrene is the dispersed phase. Here, on the right side, polystyrene is the matrix, the continuous phase, and natural rubber is the dispersed phase. Do you think that we have the same mechanical behavior, for example, when applying a compressive stress? You agree with me that it's the two same phase, the same composition, same interfacial properties, but what about the properties in for each morphology? In fact, the important parameter is the continuous phase, the matrix. In this case, the deformation will be much higher than in this case. Okay? You understand why? Because it is a continuous phase. So this is what I call the morphology. So now I refer to the first paper on the processing and characterization of polymer nanocomposites using cellulose nanocrystals. You can see it was published in 1995, so 30 years ago. And in this work, cellulose nanocrystals were extracted from tunicine. Tunicine is the cellulose extracted from tunicate. Tunicate is this sea animal. The interest in using this cellulose is that it is highly crystalline. And the polymer matrix was a copolymer of styrene and butyl acrylate in the form of a latex, so an aqueous dispersion. So the processing was very simple, just consists in mixing the two aqueous dispersion, then water was evaporated. So it's necessary to evaporate water above the Tg of the polymer. In this case, it was interesting. It's a kind of model matrix because by changing the ratio of styrene and butyl acrylate, it's possible to adjust the Tg of the polymer. And in this case, Tg was around 0 degrees Celsius, meaning that evaporation can be performed at room temperature. Also, the interest of using this copolymer is that it is a random copolymer, so it's an amorphous polymer, and there is no impact of the crystallization of the matrix. So you can see here the nanocrystals obtained from tunicine, so they are very long, the aspect ratio is high, so it's almost 70, and here's the aqueous dispersion of the latex. So the two aqueous dispersions are mixed, water is evaporated, and we obtain nanocomposite film with a good dispersion because the dispersion is preserved more or less during evaporation, even if some sedimentation was observed. Then these nanocomposites were characterized here by dynamic mechanical analysis. So you can see the evolution of the storage shear modulus. that was normalized at low temperature as a function of temperature for the pure matrix. This is in black. And it's a classical behavior for an amorphous polymer with a high modulus at low temperature, a sharp drop here, which is associated to the TG of the polymer, and then more or less a stabilization that corresponds to the rubbery state, and then the flow of the polymer. In this case, the molecular weight was quite low because, as you can see, the rubbery plateau is not well identified. Now, when adding 1 up to 12% of cellulose nanocrystals, we observe two things. The first one is a very strong increase in the rubbery modulus. When I say very strong increase, remember that we have here a logarithmic scale, meaning that here there is an increase of about 10 by adding only 1% cellulose nanocrystals. With 3%, it's about 100. And with 6% by weight, it's about a factor of 1,000. 6% by weight means 4% by volume. This reinforcing effect was never observed. And the PhD candidate, Véronique Favier, received the prize of the French Composite Society for this work because this effect was never observed. So this is the first effect. The second effect is the thermal stabilization of the composite up to about 500 Kelvin, above 1% of cellulose nanocrystals. We have this stabilization. There is no more flow. And so this is up to about 500 Kelvin that correspond to the temperature at which cellulose starts to degrade. So usually in material science, the material is characterized, we obtain some data, as I showed you previously, and to determine the morphology of the composite, or the blend, it's necessary to use a model. So it means that we know the nature of each phase, we can determine experimentally the behavior of each phase, we can make an assumption on the morphology. We can use a model with this morphology, and we check if we have a good agreement between the experimental data and the model. If yes, we can be happy. If no, we have to change something. And so there are different options. So it can be a wrong assumption on the nature of each phase, a change in the physical behavior of each phase when they are in presence, wrong assumption, of course, on morphology, or the presence of an interface. This was done, and first we use the Alpine-Cardoz model. So the Alpine-Cardoz model is a Binfield approach. Briefly, it is broadly used for short fiber composite, but also for semi-crystalline polymer. It just consists in assimilating this short fiber composite to a laminate composite with 4 plies. And each ply, we have a given orientation of the fibers. So there are some equations which are not very important, but what is important is what is considered in this model. We consider the filler geometry, the length, the diameter of the fibers, the filler volume fraction, of course, but also, and this is important, the mechanical anisotropy. This rod, this nanorods, consists of aligned cellulose chain, meaning that, of course, the longitudinal modulus is much higher than the transverse modulus. Okay? And this is accounted in this model. There is no adjustable parameter. For this equation, we use this parameter, so the aspect ratio of the nanorods, that one was determined by microscopy. This is nu m, so it's a Poisson's ratio of the matrix. So it's 0.5 for a rubbery polymer. The modulus of the matrix, which is experimentally determined, This is the Poisson's ratio of cellulose and some mechanical characteristic of these nanorods. This is the result. It represents the evolution of the modulus at 325 Kelvin. So 325 corresponds to the rubbery state as a function of the cellulose nanocrystal content. In blue, the experimental data. In green, the prediction. You can see that the agreement is not so good. It's not so good, and it's difficult to change any of these parameters. The only thing is that maybe these nanorods are longer than what is reported from microscopic observation, meaning that maybe these nanorods can connect together and they act as longer fibers. And so the next step was to use another model, which is this model, which is also broadly used mainly for polymer blends. It is the Takayanagi model, so it's a Japanese guy. And we adapt this model with the percolation approach. I will define this different term. For the Takayanagi model, you can see that we have three different phases. R corresponds to the rigid phase, so it is cellulose. S corresponds to the soft phase, it is the polymeric matrix in the rubbery state. You can see that the rigid phase is divided in two parts. In green correspond to the unpercolating nanorods, and in red, the percolating nanorod. What we call the percolating nanorods is the nanorods that form a continuous path through the sample. The percolation approach is reported here. Below the percolation threshold, no connection between the blue phase, and above the percolation threshold, can form this continuous phase. So we can use the equation, which are given by Takayanagi. What is interesting is that when the rigid phase is much stiffer than the soft phase, which is the case here, because remember, we have about 100 gigapascal for crystalline cellulose, and in the case of the matrix, we are considering the polymer in the rubbery state, so it's very low, it's lower than 1 megapascal. And so we can simplify this equation, and it's only given by this equation. In this equation, we have two parameters. Psi. Psi corresponds to the width of this phase. It is the volume fraction of the percolating rigid phase. And the other parameter, and this can be determined from this equation, below phi RC, which is the percolation threshold, or the volume fraction which is necessary to form this continuous phase. Psi is 0, no percolation. And above this critical percolation, above the percolation threshold, psi is given by this equation. So this is linked to the percolation of theory, the theory of percolation, sorry. The other parameter is GR. GR corresponds to the modulus, the shear modulus of the rigid phase. But it is not the modulus of a single nanocrystal. It is the modulus of the percolating network of nanorods. And this can be experimentally determined. For this, you just have to use an aqueous dispersion of nanocrystal. It can be cast, evaporate. We obtain a nanopaper, and a tensile test can be performed on this nanopaper to determine the stiffness of the network. And so it was done, and a modulus of 15 gigapascal was obtained. So the shear modulus is usually 3 times lower. And so we use this equation to try to predict the experimental behavior. This is the same plot as previously. Alpine-Cardo's model in green, in blue experimental data, and the prediction from the percolation approach in red, without any adjustable parameter. You can see that there is a good agreement, except around the percolation threshold, but this is normal because in the model we consider a single aspect ratio, and experimentally we have a distribution of aspect ratio. So what is the meaning of this? We can validate the morphology. Of course, you agree with me. Good agreement between experimental and predict data. So the meaning of this is that we have strong interaction between the nanocrystals that lead to the formation of this percolating network through H bonding. And so this occurs, of course, above the percolation threshold. It allows explaining both the high reinforcing effect, because we have this strong network, and also the thermal stabilization of the composite modulus. Because when the matrix flows, the material remains stiff because of this network that was formed. In this case, the formation of this network was possible just because the material were prepared by casting evaporation. It's a slow process. And during this slow process, the nanorods have time to interact and to form this continuous network. It's exactly the same thing for paper, except that in paper we use fibers, but water is evaporated or eliminated in order to connect the fiber together through hydrogen bonding and to have the strength of the paper. So this percolation approach, remember, it is given by this equation. It depends on psi, and psi is linked to the percolation threshold. The percolation threshold depends on the aspect ratio of the nanorods. When increasing the length of the nanorods, it's easier for this particle to form a continuous network. When considering spherical particle, it needs at least 25% of this nanoparticle to form a continuous network. So meaning that depending on the source of cellulose, the length, the diameter, and then the aspect ratio of the nanocrystal differ, and of course, the percolation threshold also differ. The percolation threshold is given by this equation, this simple equation, meaning that it's interesting to use high aspect ratio nanocrystals because, of course, it results in a low percolation threshold. The second parameter is the stiffness of the percolating network of nanocrystals. It has been observed by performing tensile tests on nanopapers made from cellulose nanocrystals from different origins, that there is a kind of correlation between the modulus of the film and the aspect ratio of the constituting nanocrystals. You can see kind of correlation. That can be understood because if we have longer nanocrystals, they can interact stronger. If they are short, so the interaction should be weaker. So this is another reason for using high aspect ratio nanocrystals because of the high stiffness of the percolating network. So this is an evidence of this percolation network, a work from Kalaprasad, so you have seen it yesterday. In fact, he used chited nanocrystals extract from crab shell and natural rubber as the matrix. So the processing was exactly the same as previously. We mixed the two aqueous dispersion, water was evaporated, and then we characterize this material. He performed successive tensile tests, meaning that you can see here, force elongation. The material is first stretched up to a force of 2 Newton, and then it is stretched up to a given elongation, and then this force is released. And then it is stretched again up to a higher elongation, and the force is released again, and so on. We can describe several cycles. We can convert this force elongation curve into stress strain, and of course, for each cycle and from the initial slope, it is possible to determine the modulus. So the tensile modulus for cycle Y is called EI, and then we can determine the relative tensile modulus, which is the ratio of the modulus for a given cycle divided by the modulus that was observed for the first cycle. So this relative tensile modulus was plotted, this is for the matrix, as a function of the number of cycles. Of course, it is 1 for the first cycle because of the normalization. And then you can see that it increased. It increased because it is well known that when stretching natural rubber, we can have some crystallization, which is induced by this stretching, which is called the strain-induced crystallization. So this is the reason why we have this increase in the modulus. Now, when considering the composites with 5, 10, 15, or 20% chitin nanocrystals, we have a different situation. Of course, because of the normalization, we have 1 for the first cycle, but you can see that first, the modulus or the relative modulus decreases, and then it slightly increases. The decrease in the relative modulus is probably attributed to the breaking of the continuous network of nanorods. And then, when it is totally broken, we have a slight increase, which probably corresponds to the strain-induced crystallization of the matrix. So, you understand that the mechanical properties of this nanocomposite are strongly linked to this percolation phenomenon. And this percolation effect is impacted by different parameters. The size of morphology of the nanoparticle, the size of the latex particles, the crystallinity of the matrix, presence of a plasticizer, the processing technique, the interactions between the two phases. I will show you some examples. First, regarding the aspect ratio. In this study, nanocrystals were extracted from Posidonia oceanica. Posidonia oceanica is this alga. I don't know if you have in India. In this case, it comes from Tunisia. And it can also accumulate in the form of balls in the dry state on the beach. And so nanocrystals have been extracted from the fresh alga and from these balls. And you can see that the dimensions and the aspect ratio is different. So nanocomposite has been prepared, again, with this copolymer kind of model, copolymer of styrene and butyl acrylate. You can see here the evolution of the rubbery modulus as a function of the CNC content. And what we can see is that when the aspect ratio is higher, the reinforcing effect is higher. This was because she was a student from Tunisia. I had also a student from Morocco. And in this case, we use palm tree, because there is a lot of palm tree in Morocco. And so he prepared nanocrystals and nanofibrils from palm tree. And then, again, it was mixed with polymer, natural rubber, in the form of a latex. And this is the evolution of the tensile modulus for both types of nanocomposite as a function of filler content. We can see that a higher modulus is observed for nanocomposite based on nanofibril, which was not really expected. Because remember that the modulus of nanocrystals is 130 gigapascal. For nanofibril, it's lower, and the reinforcing effect is higher. So, in such a situation, you have to think about what can be the parameters that can lead to this result. The first one was the aspect ratio. It is higher for nanofibrils. So meaning that probably we have a connection for a lower content. The second thing is that remember that nanocrystals are stiff nanorods. Nanofibrils are flexible filaments. So maybe they can form some entanglements and it can lead to a stronger connection. Third, remember that nanocrystals consist in pure cellulose. In the case of nanofibrils, we have few percent of residual hydrophobic component on the surface. Some lignin remain. So meaning that nanofibrils are more hydrophobic and it can act as a compatibilizer with the hydrophobic matrix. So we check all these points. I will just show you results for this last point. You have here the loss angle as a function of temperature. So it is dynamic mechanical analysis for composite based on nanocrystals and nanofibrils. Here, for the pure matrix, so we have a high damping, high loss factor, and it progressively decreases when adding nanocrystals. In the case of nanofibrils, you can see that it's different. Of course, there is a decrease in the magnitude, but we have a splitting into two peaks. And this is most probably due to the fact that in the matrix, we have two glass transition temperatures. The glass transition temperature corresponding to the bulk matrix and the TG corresponding to the interface in which we have stronger interaction because nanofibrils are more hydrophobic. Size of latex particles. So it's always the same type of curve. So the modulus, the rubber modulus, as a function of nanoparticle content. Two curves. The first one is, Tunisin, in both cases, Tunisin nanocrystals were used. Polystyrene co-butylacrylate, it's the first system, which is our reference. And we use also PHO, polyhydroxyoctanoate, and you can see that the size of the latex particle is much higher. And we obtain higher mechanical properties. The reason, probably here, during evaporation, of course, the latex particle cannot be penetrated by the nanorod, meaning that we have a bigger exclude volume. And so probably the formation of the continuous network is easier. This is what we can see here for natural rubber with 16% of nanocrystals. We can see more or less the latex particles, and we can see in white the nanocrystals that are around the latex particle. So maybe I can pass fast on this. This is also TDC nanocrystals, but in this case the matrix was polyoxyethylene. So it's a semi-crystalline polymer. And we can see the dynamic mechanical analysis of this material. So for the pure matrix, we have a very weak drop at TG because of the crystallinity of the matrix. And then when the polymer melts, of course, we observe the flow. When adding nanocrystals up to 10%, of course, in the rubbery state, the reinforcement effect is weak, just because the matrix is stiffer because of the presence of the crystalline domains. But what is interesting is to see that above the melting point, we keep a stabilization in the or cohesion of the material due to the formation of this percolating network. So on the right side, it's a more difficult system. In this case, it's not a latex, it's a water-soluble polymer. We use thermoplastic starch, so a mixture of starch and glycerol in this case. And of course, we expect very good interaction between the matrix and the reinforcement. And we hope to have outstanding properties. And it was not the case. You can see here, again, the rubbery modulus as a function of nanoparticle content. So this is our reference, the copolymer of styrene and butyl acrylate. And these curves are for starch reinforced with tungsten nanocrystals, but materials that have been conditioned at different relative humidity, because of course starch is sensitive to moisture. This work was done by a Spanish postdoc, and she made a mistake. She used a huge amount of nanocrystals. You can see 18% by volume, so it was 25% by weight. We never use so much amount. But even for this amount, you can see that the reinforcing effect, there is nothing. And again, you need to think on what happened. I tell you it's a complex system because starch is a matrix. Starch is a semi-crystalline polymer. This is one thing. We had a plasticizer, glycerol, and usually the plasticizer is not homogeneously distributed, meaning that we have two phases. Glycerol-rich domain, which are here, with a low TG, and amylopectin or starch-rich domain with a higher TG. We had cellulose nanocrystals. Of course, we have cellulose, we have starch, we have glycerol, we have water molecules. And you can understand that there are some interaction or competitive interaction between all these components. So we try to characterize the interaction between these different components. For this, we determine the contact angle for both water and glycerol on a surface made of starch, amylopectin, or cellulose nanocrystals. You can see the contact angle here, for which solid surface the two liquids have a better affinity. Is it cellulose or starch? Cellulose. Because when the contact angle decreases, it means that the affinity of the liquid for the solid is higher. So it means that most probably what happened, we have the cellulose nanocrystals, some water, some glycerol, and they are attracted by the surface of cellulose. And of course, because of the coating of the nanocrystals with this soft interface, it's not possible to form a continuous network. No reinforcing effect is obtained. We perform also another analysis, which is a measurement of the glass transition temperature. So remember that we have a two-phase system. The matrix consists of glycerol-rich domain with a low TG and starch-rich domain with a higher TG, which are these two TG, which are reported here, for different cellulose nanocrystal content. And this TG is plotted here as a function of the water content. We can see for the glycerol-rich domain that we have a plasticization effect, meaning that when adding water that can act as a plasticizer, there is a decrease in TG. For the amylopectin-rich domain, for 0 and for 3% nanocrystals, we have this plasticization effect. But for higher nanocrystal content, we have an anti-plasticizing effect, which is probably due to this migration of water and glycerol. And of course, the starch matrix has less water and less glycerol. Now regarding the interactions between the matrix and the nanoparticles, this is an example in which a copolymer was used, so it's a polyvinyl alcohol covinyl acetate. So with some OH groups, which are hydrophilic, of course, and some acetate groups, which are more hydrophobic. And we can change the ratio of these two monomers, and by plotting the modulus, or in this case, the relative modulus, for composites that were stored as 0% relative humidity and with 12% nanocrystals, we can see that there is an increase in the modulus when increasing the degree of hydrolysis or the number of OH groups in the matrix. So this is an interesting work also that has been performed by a colleague in the University of Fribourg in Switzerland. They try to mimic the dermis of sea cucumber. So sea cucumber is this animal. It can be very soft, but very fast it can be very stiff. And this is due to some nanorods made of collagen. And he tried to mimic this behavior, and for this he used tunicine or tunicate nanocrystals and this copolymer as the matrix. So the material was performed, the mechanical properties were determined, and you have here the modulus, so it's always the same curve, the modulus as a function of the volume fraction of the filler. This behavior was observed for the dry nanocomposites, so it's this black square, and it was well fit with the percolation approach, and this material were swelled in water. And after swelling, you can see that there is a strong decrease in the mechanical properties. The reason for this is that there is a decoupling of the stress transferring rigid CNC network when introducing water, because it is a competitive hydrogen bonding agent. The water molecule inserted between the nanocrystals disconnects the nanocrystals, the network, and the mechanical properties drop. And then after swelling and drying, can recover the same mechanical properties. And so to see that it's really this phenomenon that was involved, it tried to swell the material in isopropanol instead of water, because isopropanol swells the copolymer similarly to water, but it cannot disperse the CNC. And you can see the result. For the materials that were swollen in isopropanol, we keep the same stiffness. I come back to this figure. We have seen that it's possible to use aqueous medium, water-soluble polymer, or a latex. But of course, it limits the number of polymer matrix that can be used. And to broaden this number, we can think about non-aqueous suspension. If the nanocrystals or the nanofibril can be dispersed in another liquid in which a polymer can be soluble, we can use the same process, but not with water, but with another liquid. And this is possible for some non-aqueous polar medium, for some solvent mixture, or we can proceed to a solvent exchange. We can use surfactant or chemical modification. And again, we can use the same processing technique. Use of an adequate solvent. It was shown that nanocrystals can be dispersed in different polar liquid medium. Solvent exchange, so it consists in just replacing water with acetone, and then acetone with, for example, toluene, if you plan to use natural rubber for the matrix, can be another liquid, of course. You can progressively decrease the polarity of the liquid. This is an example of non-aqueous suspension. We can see a photograph of dispersion of nanocrystals observed in polarized light. This is in water, this is in DMF, and here in different liquid. And to check if we have a good dispersion of the nanocrystals, we can see this birefringence which is the formation of these domains, organized domains. Now regarding solvent exchange. So CNC aqueous suspension can be solvent exchanged by several successive centrifugation and redispersion operation with sonication after each solvent exchange to avoid the aggregation. Sometimes it works, sometimes not. You have an example here. Cellulose nanocrystals extracted from sisal, microfibrillate cellulose or cellulose nanofibril also from sisal. In water, stable suspension, acetone, the suspension is also stable. Dichloromethane, it is less stable, but it is more or less stable for nanocrystals, but not for nanofibrils, probably because of entanglements between the flexible filaments. Yes, maybe I can show this rapidly. It's also a work from my colleague from Fribourg, Christophe Weder. It's an high process, but it's very long. It takes at least 1 week to prepare the nanocomposite. It consists in using a dispersion of nanocrystals, so T here stands for tunicate, to proceed to a solvent exchange that should be soluble with water, so usually acetone is used, and we have a gelation, so progressively we have an exchange between the two solvents. Then, so this is this, the gel CNC scaffold, which is embedded, no, sorry, this is another step, sorry. So the upper face can be removed. We can keep this organogel, which is deep in a polymer solution. So the solvent needs to be soluble also with the solvent which is used here. So you can see that there are some restriction. And after 7 weeks, we have a progressive exchange. And the polymer can penetrate into the network of nanocrystals. And then this material is hot pressed to obtain a composite. It's good, but you see that there are some limitations and the process is very long. Come back to this slide. Use of a surfactant or chemical modification. We can coat, of course, the surface of the nanoparticle with a surfactant. The problem is that the specific surface area is high, meaning that the amount of surfactant is also high. Chemical modification, we already discussed this. It involves the OH group from the surface. So you probably know that there are different types of surfactants. Remember that cellulose nanocrystals are negatively charged because of the sulfate group, meaning that usually cationic surfactants are used. So these are different cationic surfactants. Another thing that can be used, which is similar to a surfactant, is the use of copolymers. In this case, a tri-block copolymer consisting of polyethylene oxide, which is hydrophilic, and polypropylene oxide, which is more hydrophobic. This kind of polymer is called pluronic polymers. It can be used, it's like a surfactant. In fact, it's a non-ionic surfactant. Chemical modification of the surface. So it impacts the OH groups. We have seen that we can graph small molecules, longer molecules, but there are two conflicting effects. Of course, we can improve the dispersion of the nanocrystals after hydrophobization in an apolar liquid. But at the same time, because of the grafting of this molecule, the interaction between the nanocrystals are limited, meaning that the formation of the network is more difficult. This is an example. It's again calaprazade. The storage modulus as a function of temperature, so it's still for chitin nanocrystals and natural rubber, pure matrix, 10% nanocrystals. We have seen that we have a strong reinforcing effect because of the formation of the network. And the same chitin nanocrystals were used after chemical modification with 3 chemical agents. And you can see that for the same amount, 10%, the reinforcing effect is much lower. That seems contradictory to microcomposite, because for microcomposite, when we compatibilize the reinforcement and the matrix, the mechanical properties are increased. In this case, you understand that what we want to promote is the interaction between the nanocrystals. And if we have a good adhesion between the reinforcement and the matrix, of course, it is at the expense of the interaction between the nanocrystals. But for this, of course, it's necessary to have a good dispersion. So, another approach that we briefly discussed yesterday is the grafting of long chain of macromolecule. So it consists in transforming the nanoparticles into a co-continuous material through long chain surface chemical modification. So it's necessary to use, of course, a grafting agent that bear a reactive end group. It will react with the OH group from the surface, and a long compatibilizing tail. So the objective is to form a continuous interface between the filler and the polymer matrix that can improve the interfacial adhesion, but not too much destroy the interaction between the nanocrystals. And in addition, we can have some entanglements between the graphed and ungraphed polymer chain, which are, if the molecular weight is high enough, of course, that can even improve the mechanical properties, and we can have a co-crystallization. We already discussed this briefly. This is the two strategies for polymer grafting: grafting onto, grafting from. Grafting onto, the nanoparticles are mixed with a polymer, a coupling agent, and the polymer is grafted on the surface of the nanoparticle. So the good thing is that the polymer can be fully characterized before grafting. We know the molecular weight of the polymer, but of course the viscosity of the medium is higher because of the polymer, and there are some problems of steric hindrance. The other strategy, grafting from, consists in mixing the nanoparticle with a monomer and an initiator, and the polymer grows from the surface. Of course, the reaction is faster and easier, non-steric hindrance and low viscosity. But the problem is that the graft polymer cannot be fully characterized. It can be, of course, it's necessary to detach the graft molecule from the surface and then to analyze this material. So, I think it's time to conclude. Water is the preferred processing medium for polysaccharide reinforced bio-nanocomposite, and this is due to the stability of aqueous dispersion of nanofibrils, nanocrystals. The use of a water-soluble polymer in the form of a latex is recommended, but of course it limits the number of polymer matrix. Stable non-aqueous dispersion of polysaccharide nanomaterial can be obtained and used to prepare nanocomposite by casting evaporation using another liquid. The formation of a percolate network through hydrogen bonding interaction between the nanoparticles is responsible for a significant improvement in the nanocomposite mechanical performance. Some requirements. Of course, the first thing is that the nanoparticle must be uniformly dispersed in the polymer matrix. If you have aggregate, you cannot expect any reinforcement. The CNC content in the nanocomposite must be above the percolation threshold. That depends on the aspect ratio of the nanoparticles. The formation of the network is not affected by factors such as water, which is the case for the sea cucumber, you remember, CNC surface treatment, interaction among the nanocrystals, and also, I didn't discuss this, but orientation of the nanocrystals, we will discuss this later, morphology and chemistry of the matrix. And the matrix should be in the rubbery state. Thank you. I don't know if you have any question.
Thank you, sir. Now the session is open for discussion.
Thionic liquids.
No, not myself, but most probably some have tried. Now we have tried, I will show you later, we have tried some quaternary salt. And yes, it worked, but it's always the same story. But I don't want to say what happened in the next hour, but it's always the same story. If you want to avoid aggregation, for this, you need to block the OH group from the surface. And if you block the OH group from the surface, you cannot form the continuous network. It's difficult.
Sir, in slide number 19, no? You measured the
Slide number 19.
19. Sir, you measured the water contact angle measurement of CNC, no?
Yes?
Sir, how do you...
In fact, we can determine the water content by controlling the relative humidity. The material was stored at different relative humidity, and then we can determine the water content in each case.
computational method, sir?
Sorry?
Is it a computational method? Computational method.
It's a, sorry?
Is it a computational method?
No, it's not computational, not at all. When you have, you can determine the water content of a polymer or material in general. You can evaporate the water and you know the water content.
Okay, water content.
Yes.
That is, okay, fine, sir.
I didn't mention, and it's good from this slide because you are a younger researcher. In this case, you see that the results were very bad. No reinforcing effect. We expect a reinforcing effect, no reinforcing effect. And so you can see, okay, I will not publish. But if it doesn't work, and if you can provide some explanation why it is not working, you have to publish. This publication is one of my most cited publications. And it doesn't work. We didn't obtain what we want. So, bad result or bad result, not expected result can be important.